So you think you can tell an atom from an isotope by just a funny smell? We've been over these same old things. We all need to be able to use the periodic table. All right, welcome everybody to this week's edition of Video Notes for Mr. Pflugen's chemistry class. And this week we'll be talking about atoms, ions, and isotopes, so different forms of atoms and the particles in them. These notes will go on page 24 in your chemistry notebook. Thanks for tuning in. Let's get started. So let's talk about the periodic table. All right, as we look at an element in the periodic table, basically that square, that box, which has the atomic symbol, the atomic number, the average atomic mass, and maybe a couple other pieces of information in it, represents the most common form of that atom. All right, the atomic mass, in fact, is just an average, right? It's an average of all of the types of that element, okay? And those are known as isotopes, which we'll talk about in just a moment. All right, but there's also ions and sometimes elements when they're in their base state, such as oxygen, form molecules as well, diatomic molecules. So, this periodic table just shows us the basics, right? So we need to start figuring that out. Now, the way the periodic table is arranged is by atomic number, right? So if you work your way from left to right, all of them are in order by their atomic number, although they've been arranged into groups so they can represent common characteristics and electron structures. All right, well, let's keep going here. All right, well, let's talk about isotopes first. Okay, this is kind of an important idea because it tells us why there's average atomic masses on the periodic table. Not all atoms of the same element have the same mass. That's because they're isotopes, right? When we look at an isotope, right, that means that there's more or less neutrons, and that changes the mass. Down here we have an example. There are 3 different isotopes of hydrogen. All right, hydrogen 1, which has no neutrons, hydrogen 2, which has 1 neutron, and hydrogen 3, which has 2 neutrons. Now, which isotope of hydrogen would be the most common? Well, the average atomic mass of hydrogen is 1.007. So as we look at this, which one would be the most common? If you answered hydrogen 1, you're correct, because the average atomic mass is closest to 1, right? Hydrogen 2 and hydrogen 3 are much less common. Okay, that's why the average mass is only slightly more than 1. Part of the reason for that is this: as we start adding neutrons and making nuclei bigger, they become somewhat unstable. That means that those atoms don't hang around very long in that state. All right, so let's talk about the other I word we're going to use today. That's an ion, right? And basically, ions form when atoms gain or lose electrons. All right, and the reason they do that, and we'll talk about this more when we get to chemical bonding in a couple of weeks, is that they need to become chemically stable. All right, in order to be chemically stable, an atom needs a full outer electron level. So let's take a look at a couple of examples to maybe explain this. Lithium has only 1 electron in its outer level. So generally, lithium will lose that outer electron. So that one will go bye-bye. What happens then is this: there's 2 electrons left in the atom, but there's 3 protons in the nucleus. Overall, because we lost a negative charge, it leaves the atom positively charged, right? On the other hand, we have something like fluorine, which needs 1 electron to fill its outer level. It will often take or gain an electron, all right? What that'll do is then you've got 9 protons, but 10 electrons, giving the atom overall a negative charge. So gaining electrons means it becomes negative, losing electrons means it becomes positive. All right, so when we talk about ions, we need to notate those and show those. So when we do that, We do that by putting the charge as well as the number, if needed, as a superscript up above the chemical symbol of the element. So lithium, like we talked about, is a +1 charge, right? So we just put a little plus. The 1 is kind of implied, right? Kind of like when you're writing 1x in math, right? You don't put the 1 in front of it. The 1 is implied. Same with fluorine. Since it gained 1 electron, it becomes a -1. Now we have other elements that might gain or lose 2 or more electrons, right? So magnesium, it usually loses 2, so we put the 2 as a superscript next to the plus. Oxygen tends to gain 2, so we'll put the 2 as a superscript next to the minus. All right, so we talked about changing neutrons makes isotopes. Changing electrons makes ions. What happens if protons change? Well, a proton is like the DNA of an element. If you change the protons, you change its identity. Just like with us, if we had different DNA, that would probably change our identity, right? We would be somebody different than who we are. Okay, so same case here. When we change protons, it becomes a different element, not a different charge. For example, okay, if you have 5 protons, that's boron, right? If it lost a proton, what element would it be? Well, if you answered beryllium, you would be correct. If it gained a proton, what element would it be? That'd be 6 protons, right? In that case, that would be carbon. So protons are important in identifying the characteristics and the identity of the atom. All right, change protons, change the element. All right, let's talk about Bohr models real quick. The only reason that we use these is because it shows electron energy levels. And those are important as we start talking about bonding and things like that. Okay, so the first level has up to 2 electrons, the second up to 8, and the third has up to 18, although technically only 8 is what we worry about. You know, we'll get into that later as we talk about electron structures, all right? Let's do one for carbon real quick, okay? We've got the nucleus here in the middle, right? And then let's start doing our rings. So there's one ring, okay? And we've got 2 electrons on it. Once we have that, it's full. So we need to go up to the next ring. Carbon is element number 6, so it has 6 electrons. There's 1, 2, 3, 4. So there's a very sloppy finger-drawn Bohr model of carbon. Okay. Now as we get to magnesium, I'd like you to do this. Magnesium is element number 12. I'd like you to just quickly sketch a Bohr model of magnesium on your paper. Okay. Fill from the bottom up. So the first level should have 2, and then work your way out from there. How many electrons are in the biggest energy level, the highest energy level of magnesium? All right, so Lewis dot diagrams, all right, these are going to be vital for us as we get into structures of compounds, all right? Now when you do these, there's only 8 spots available. Think of an invisible box around the letter, and there's 2 spots on each side, all right? That's the maximum available. But we only want to show the electrons that are in the highest energy level. So think back to the last slide, right? Carbon. Okay, carbon has 4 electrons in its highest energy level. So we do this. We go 1, 2, 3, 4. Just like that. And I tend to work my way around clockwise. You don't start pairing up the electrons until you have to. All right? So the other one we did on the last page, I asked you to do this, was magnesium, right? Magnesium only has 2 electrons in its highest energy level. So we do this. 1, 2. Okay. Now chlorine's a little different. All right. If you figure out chlorine, chlorine has 7 electrons in its highest energy level. So I do this. We go 1, 2, 3, 4. Now we have to start pairing them up, right? 5, 6, 7. Okay. So there's 1 empty slot there on chlorine. Okay. And we'll be working on these more and more. And also, if you can't remember, there is a pattern on the periodic table that helps us figure this out. Well, thanks for tuning in, folks, and I hope you have a great day. We'll see you in class next time. Bye-bye.